All right, welcome to this video where we're going to do a quick introduction to the way that trees are used computationally in computer science. And we're going to look at some of the terminology used to describe trees. So to start out, obviously trees are inspired by trees in nature. So here I have just sort of a depiction of a sprawling tree with a lot of branches and leaves. And we're going to use this inspiration to describe the tree data structure, although it's not just one data structure, there are many data structures that are trees. And trees in computer science are not just data structures. There are recursion trees, which are express the sequence of operations carried out by a recursive algorithm. Trees can be used as a data structure, but might also be used within an algorithm. Huffman trees are used as a part of compression. Game trees are used as part of maybe selecting a move in a game like tic-tac-toe or chess or checkers. So all these different types of trees that exist in the computational world are all inspired, of course, by biological trees, but not just biological trees. Another place in the real world where we find sort of trees is in the realm of family trees. So another area where a lot of our terminology we're going to draw from are from family trees. And so here I've got one family tree depicting the Skywalker family from Star Wars. Of course, this family tree is very complicated. It doesn't just show depictions of parent to child, which is the standard relationship depicted in a family tree. Here we have adopted parents. Here we have masters and student. This is maybe a trainee chart as well. So another tree you could have is one that ranks mentors with their students, and this would be similar to a family tree. Well, here I'm bringing this in as an example just to say we're going to use some of the terms that we would normally use in a family tree to also describe computational trees. And perhaps I'll come back to that a little bit later. Family trees are a little bit more complicated than computational trees, but that's maybe something more for genealogy than it is for computer science. Here's just another example I wanted to pull of a tree being used in a realm outside of computer science. And in this case it's in biology. This is called a cladogram, which is used in biology to categorize species based on how closely related those species are, based on a variety of different measures for closeness. And here, by branching them by closeness, we can use that to maybe predict how long ago it was that those two species shared a common ancestor. So for instance, humans and chimpanzees, our closest living ancestor or closest living relative, it's expected that we shared a common ancestor somewhere between 2 to 6 million years ago, a long time ago. So maybe that's what some of these numbers here are indicating. Of course, I'm not an expert in this area, so but this is just another case where trees have been used, and this one relates a number of different creatures. Here we have some sea mammals. These are all mammals, it looks like. We have some sea mammals and how they are related to other mammals. It looks like here that these sea mammals, dolphins and such, seem to be more closely related, at least according to this category, or at least this classification. They seem to be a little bit closer to hippos than they are to maybe, these look like gazelles of some kind. We have camels down here, zebras, and it looks like the furthest away that it is related to, notice everything in this graph is still related, they're all mammals, but the furthest away one, at least living one, it seems to is the wolf here, and that one it looks like, so I guess you'd have to add all these numbers up to determine how many million years ago that was, or maybe these are thousands of years, I'm not certain. Those two species shared a common ancestor. So these are, again, just another way that trees might be used in other fields to hold the data here being the species and these numbers. Okay, so in computer science, where it's our role to create the structures that hold the data that might be relevant in some of these other fields, we have a number of different data structures, tree data structures, that we might use. And probably one of the simplest and most commonly used ones is a binary heap. And this is an example here. The binary heap follows a very simple rule where for any given node in the heap, the children node must be greater in value, whatever values are stored in there. This would be for what's commonly called a minimum heap. We can switch that rule around so that the children must be less than, and then we'll get a maximum heap. And the properties of a minimum and maximum heap that we find relevant are that a minimum heap will always keep the minimum element on top. We see that here. And a maximum heap will always keep the maximum element on top. And those are valuable in some algorithms. And we'll take a look at that in a future video. We can look at another very common tree, binary search tree. And the rule for a binary search tree is also pretty simple. It's the values to the left must be less than the value in the node, and the values to the right must be greater than the value in the node. And of course, if you satisfy that principle, then we will say that you are a binary search tree. And here we have an example of one. And binary search trees have a couple of important properties. One is that an in-order traversal of them will return the elements in order. That's something we'll look at in a future video as well. And another property is if you want to search a binary search tree for an element, the search mimics the binary search algorithm. So if you're familiar with that, then you might already know how a binary search tree operates. This is an example of another type of tree you might encounter in computer science called a trie. And this tree in the trie, we will store words that are created as strings or sequences of characters. And this one might have been used to count the frequency that words were encountered in a document. For instance, here the word just the word a, may have been encountered 15 times, whereas the word t maybe is only encountered 3 times. Here we store the value down in the tree by following the letters T, E, A to find the word that we find. Now, tries are used in a number of different algorithms as well. Here's another example of a tree. This is called a Huffman tree. Now, a Huffman tree is not necessarily a data structure where we would store data. It's instead a tree that we construct as part of an algorithm to encode text data. And so here I've got an example that we'll look at in more detail again in a future video, where we've encoded some text data that has 8 symbols in it, A, B, D, H, I, N, S, and space. And we've encoded it using this encoding scheme that we've got listed here that we derived by applying Huffman's algorithm, which creates this Huffman tree. And the final example of a tree that I want to show here, this is called a B tree, also known as a 2-3 tree, this variant. A B tree is a generalization of a binary search tree. So you can actually carry out binary search on this in the same way and get your find the element you're looking for. But this is generalized to more than one element stored in any particular node. And again, we'll take a look at this in a future video. So I now want to look at some of the terms that we use to talk about trees. I've already used some of these terms quite naturally in describing some of the example trees we were just looking at. And to do that, I'm going to use this tree here as an example. This, as it says here, this is a tree. It's actually a special kind of tree. It has a few extra properties that we'll go into more detail about. But one is it's a binary tree, and that's the most commonly used type of tree in computer science. And it's also got an interesting property that we might define in a bit, but we can see that it's kind of filled up. It's filled, and every node has two children, except on the bottom level where they're all of them have 0 children. So it's sort of a full tree. And I'm going to use that to, one, introduce our terminology, but then later on we're going to start looking at properties of trees that look like this, that have all the nodes in them. Okay, so I guess I've used the term node already quite a bit. So a tree consists of nodes. We sometimes call them vertices. That's sort of more of a graph theoretic term. And they're connected together using edges or connections. In trees, typically it's the nodes that are more in focus, but the edges also are relevant to some calculations. And we borrow a lot of our terms from family trees and the notions related to familial relationships. So a node, here indicated in green, can have a parent, indicated in red, or it can also have children. And again, I've sort of used these terms already, but here the green node has 2 children. In a binary tree, we'll often call these the left child and the right child. And again, we can extend that to the notion of having a grandparent or grandchildren as well. So these notions extend. In addition, a node we might say has a sibling if we share parents, or cousins if we share a grandparent. And we could extend that to this is first cousins, we could extend that to second cousins and so on, although we try not to we don't go too much further if we don't need to. It's the same with great-grandfather, great-grandchild. We can extend all these as far as we need to, but usually we limit discussion to be within pretty close by. And the other term that really is kind of important is the sibling of a parent, which we'll usually call a great, or an uncle, whereas a sibling of a grandparent might be called a great uncle, and so on. So again, we can extend that definition out. So these are just ways to talk about how nodes in a tree might be related to one another. And we can actually extend that again further. So my parent and their parent and so on, all of this chain of individuals will all be the node's ancestors, whereas the collection of all of the node's children or its children's children and so on are its descendants. Okay, so all those terms were sort of borrowed from the notion of family trees. Now we can look at some terms that we can borrow from the notion of just biological trees. The first node that we might introduce would be the root node. This is usually a privileged node or important node in a tree. It's the node that has no parents. What that means also is if we are storing this tree in memory somewhere, then this is probably the node we have a reference to. This is the root node, the base of the tree. Maybe it's important to note here, it's been pretty clear looking at it, but trees in computer science grow down, opposite from trees in nature that grow up. So the root here is on the top of the tree. Of course, we call it a root. Other possible names like a stem or a trunk, we don't use those. Root is by convention what we call it. The opposite of a root, I guess, then are leaves. Leaves are the ones at the end of the branches, if you will. They have no children. A leaf has no children. So that's the definition, again, that we would apply there. And all of the other nodes that are neither a leaf nor a root we might call interior nodes, or sometimes branch nodes, though that's less common. We might call them a branch node when, specifically when this is something we might call a decision tree, where at each node we have to decide to go left or right, something like that, and we traverse the tree in that way. Then we might emphasize that they're decision nodes by calling them branch nodes. So when we start doing analysis on trees, analysis of a tree's shape, analysis of algorithms that rely on trees, or analysis of operations carried out on trees, there are going to be a number of different properties of trees that might become relevant. So here, if we're interested in accessing this node here, again the node indicated in green, we might have to traverse down to find it, and to find it we need to follow a path. And so a path here is going to be a sequence of edges connecting to two nodes. And in this case, I've indicated a path that connects the root node to a selected node. And we can actually use this notion of a path to come up with a definition, a more formal definition of what a tree is. Some take a definition to a tree to be in a tree, there's going to exist exactly one path from the root node to any node. And we can see that that's going to be true for any of our nodes here, or for this node we've selected, there's only one path from the root node to that node. And more generally, in a tree, if that follows that definition we just applied, for any tree satisfying that, we also have the fact that for any two nodes in that tree, there should only be one path between those two nodes. So here again, I've indicated a path between two nodes, there is only one of them. If the node is not an ancestor or descendant of the other node, then this path must pass through a shared ancestor. So we can see here that our two nodes are actually cousins, and they share a grandparent. And actually, in this case, we have a special case where the grandparent, the shared node, is the root. There are a couple other important definitions related that will be important to our analysis. We call them the depth and the height, and they're sometimes confused or conflated because sometimes they are the same. But at first here they are not, so let's see the differences. So here we have the depth of a node is going to be the length of the path from the root to the node. Now here we have sort of a subtlety. Are we going to count the edges on the way down or the nodes on the way down? We can see in this path I've indicated here there are 3 nodes but 2 edges. If we count the edges, this is a 0-based counting, and if we count the nodes, this is a 1-based counting, and this is just something we need to decide when we're talking about our depth. And how we decide which one we're going to use usually is dependent on the purpose that we're going to put the depth to. For a lot of the calculations we're going to make, 0-based depth is going to be more useful. Of course, we could translate them into 1-based depth, but then there would be a -1 showing up in our calculations, and usually we might want simpler calculations, so to avoid that, we'll just shift to 0-based depth calculations. Okay, we can also do the height of a node. The height of the node then is the length of the path from the node to its deepest leaf descendant. So we sort of use the definition of depth here to define height. But for this particular node, all of our leaves are of the same depth, so any one would work. I've just selected one here. Again, we can see that for this path, there are 3 nodes or 2 edges, depending on how we count, and it's going to be the same for height as it was for depth. Now we can use those definitions to define the height and the depth of a tree now, and the height of the tree then is just going to be the height of the root, and then the depth of the tree is just the depth of the deepest leaf. Now you'll notice that those are parallel definitions, they're the same, and so what that means is the height and the depth of a tree will always be the same, which maybe makes sense. As a result, this is one of the reasons why we will sometimes confuse the height and the depth of a tree because they're usually the same. And for a tree they're the same, but for the nodes they are not. And so we do want to make sure we keep that distinct in our mind, that while sometimes we'll get used to interchanging them when we're talking about trees, when we switch into talking about nodes, we want to keep them very distinct. All right, the final term I want to define is also a very useful, helpful one, is the subtree term. Here, a subtree is usually indicated by selecting out a node in the tree as a root. And so we'll say that this is the subtree rooted at the node. It's going to be that node and all of its descendants. And again, very straightforward, but again, a term that has a specific meaning that we can now use, say, in a proof or in a description of something more complicated. All right, those are all the terms I actually wanted to cover in this video. That's not all the terms that one could define related to trees. There are, of course, numerous terms related to trees, but those are a lot of the common ones that you will find in most descriptions, and the ones that we're going to use in the next couple of videos to talk in more detail about trees. The next thing I want to do is I want to look a little bit closer at binary trees in particular, but something called emery trees. And we're going to look at some of the mathematical properties of emery trees in the next video. So thanks for watching, and we'll see you in the next video.